Meteor crater, iron object hits the ground. And I want everybody to ponder this little statistic here, this sense of relative proportionality that I'm about to talk about here. Objects the size of Tunguska, or I mean the density of Tunguska, they might be the same size, 150 feet. This one hits the ground, leaves a big hole in the ground. We can come by 50,000 years later, look at the hole, find the pieces of the object, makes it pretty damn clear what it was, right? Over here, it blows up 5 or 6 miles up in the air, right? If it blows up over a forest, like in this case, about 825 square miles of old-growth taiga forest is just flattened, right? Because of this, the pressure wave coming down from above, literally, and then spreading out laterally. And that's why under the epicenter of Tunguska, like a ring around it, is a group of standing trees that have had their branches stripped off vertically from the vertical shear forces of this blast wave coming down. It then moves outward. So the trees on this side of the epicenter are pointing this way. The trees on this side are pointing this way. Pretty damn obvious to Kulik when he first arrived there in the late 1920s. Leonid Kulik, when he arrived there, he was the first scientist to make it there, right? So he was pretty damn impressed. I think I read his from his journal, his diary last episode, how unsettling it was to look that as far as the eye could see, this whole forest is just flattened, right? The magnitude of that blast is extremely impressive, right? So here's the thing, though. In the late 1920s, it was obvious. You go there now, it's not as obvious. Now, to the trained eye, knows what they're looking for. Yeah, you will find remnants of the forest that was blown down. You can actually find genetic anomalies in a lot of the plants that are post impact, right? You can find where there are very small microscopic spherules embedded in some of the trees that did survive because of the blast wave carrying these microscopic particles, actually embedded them into the cambium of the tree. As the tree has grown, if you drill into the tree and you pull out a core that goes back to 1908, you can find that microscopic evidence, that fingerprint right there, see? But what would happen if you come back 1,000 years from now, or even another century or two? Guess what? You're not going to probably even know to even look to see if anything ever happened there, such as a bolide impact. Certainly 1,000 years or 2,000 or 3,000 years from now, people could be, living there. They could have huts. They could have villages. There might even be a city. Nobody's going to even know what happened there. So there's a whole class of cosmic encounters that don't leave the lasting footprints that I'm talking about, you see? And so when you try to derive the, statistical probabilities of impacts, a lot of them up to this point have been based on crater counting. Well, if you're only crater counting, you're missing this whole class of impact-related events, right? Now, when you begin to look at the ratios of, let's say, the dense objects to the low-density objects, these low-density objects, the ratio is like 10 to 1. So think about that for a minute. There could be, just that alone implies that there's probably way, way, way more Tunguska-type events than had been considered. And there are some that are looking at this that are going, yeah, let's see. The low-density objects are much more abundant than the high-density objects. So if we're looking at things that are, 150 up to, say, 1,000 feet in diameter, well, then the low-density objects might not be leaving those obvious footprints in the ground that we can find thousands of years later. And then from that derive assessments of the probabilities of encounters. You see what I'm saying? So I think one of the important insights that we really need to be thinking about here is that, yeah, there may be a whole lot more of these encounters, Tunguska-type encounters. And if there is, hey, that's important to figure into our planning. Because a lot of the planning, particularly back in the post, 80s, 90s, even into the 2000s, the probabilities of impacts if you look at how they're derived, a lot of them, if not most of them, are derived from crater counting. Now, the thing that Victor Klube and Bill Napier and Will Asher and those guys have been looking at for about 30 to 40 years. Let's see, I think Klube and Napier's first book that I read, Cosmic Serpent, came out in 1980. So that's 40 years ago, or maybe 81. So right in that very early 80s, right? Right around the time that the Alvarez team was discovering the iridium signature at the KT boundary, right? So in that book, and ever since, they have been amassing the evidence and making the argument that there might be times in history, there are certain epochs where Earth regularly encounters much greater density within some of the auspicious meteor streams, the clumps, you will, because all meteor streams ultimately come from the disintegration of comets, right? So if you got a comet, it's going around the sun, it's going in its orbit around the sun, and each time it's passing, let's say, the sun or passing nearby Jupiter, the gravity field literally begins to take it apart. Now, it can be gravitationally induced fragmentation or just something, within the comet nucleus itself, because the comet nuclei are loaded with volatiles. So you might have major discharge and spalling events that happen even when it's not necessarily in the vicinity of Jupiter or the sun. But in any case, each passage around, it's discharging part of itself. And ultimately, it'll just keep discharging and discharging as it goes around until it's fragmented into dust, right? In that process, it'll form a dust stream. That dust stream will ultimately be swept up by the planets. If it's still in the form of a coherent nuclei, its chances of falling into the sun are pretty great. The sun is the big vacuum cleaner that sucks in a lot of these comets, and there's way more comets than anybody had realized that are falling into the sun every year. And this is something that became obvious once we had some of the solar observational satellites operational within the last 20 years. One of the unexpected discoveries was the number of sun-grazing comets that existed out there that nobody was seeing. And obviously one reason you don't see them is because they're you see them in the direction of the sun. And then otherwise, when they're out there in their pre-orbit, they're going to be really almost too small to detect. But there have been a regular succession of Halley-sized nuclei that have seen falling into the sun, right there when they're making their perihelion passage. Now, a Halley-sized nuclei is maybe 10 miles in diameter. So the whole point here is that what Klube and Napier were getting at is that there will be these episodes where a comet comes in and they actually begin to theorize the possibility of a giant comet nucleus that might have been 60 to 80 miles in diameter, making entry into the inner solar system and becoming Earth crossing somewhere between 25 and 30,000 years ago, right? And then it began to undergo a hierarchy of disintegrations. Well, it takes a long time. It takes multiple passages, multiple orbits for this material to get uniformly distributed around its orbit. So right now, the Earth passes through the Taurid meteor stream twice each year, once in late June or early July, and again, late October or early November. In fact, interestingly, the November Taurid meteor stream peaks right around Halloween and the couple of days after. It's for that reason they've often been referred to as the Halloween meteors. We're going to get into and looking at some of the very interesting connections, say, between the origins of Halloween and the correlation in time with the Taurid meteor stream, but that's for a later discussion. But in any case, the idea is that the material is not uniformly distributed throughout the orbit, so there are clumps, there are clusters. If it so happens that the Earth is passing through the stream when the clump is there, you have an enhanced probability of impact or encounter events. So one of the things that they then did was by studying, as a consequence of studying the architecture of and life cycle of comets, is they realized that there would be these epochs of enhanced impact probabilities, and that there actually may be times when Earth encounters a swarm of Tunguska-like objects, creating literally a cosmic storm of these things raining down upon the Earth. And let's say you have 100 Tunguska objects. Well, now you're talking about something that's going to be as devastating as an all-out thermonuclear war. Yet, 1,000 years later, what are you going to find other than microscopic evidence? And here's the thing, that microscopic evidence might be there, just like with the Younger Dryas boundary layer. It's been there for decades and decades. It's been there for whatever, 13,000 years, right? But unless you go look for it, you're not going to know that it's there. I mean, when you walk into a room, are you going to think, you're thinking about, I wonder what the fingerprints are on that doorknob right there? Unless you're thinking about it and you have a reason to look, you're not going to see it. See, now, the thing is, when Richard Firestone went and began to look at that Younger Dryas boundary, it was because he had a reason to. Because Vance Haynes had pointed out that at this boundary was where, at 70-some sites where you had a boundary, or at least 50-some sites where you had a discernible boundary, well, you had megafauna below it, but not above it. You had Clovis culture below, but not above. So, and then when the Greenland ice cores started coming out in the early 90s, and you could correlate and go, look, right there at the Younger Dryas boundary, you have this massive spike. You have this massive warming spike followed by an equally rapid, almost plunge in global temperatures. So now you got megafaunal disappearance, you got you've got an abrupt climate shift, and you've got Clovis culture disappearance. Well, now you got a reason to go back and take a closer look. So Firestone went back and took a closer look, and that's when he started finding the impact proxies right there. So now he comes out, publishes a paper, causes a big stir in the scientific community, and then there's a group that looks at it and go, no, we can't, no, we've got this figured out. Human hunters took out the megafauna, right? It was climate change that, whatever, or it was climate change. Those were the two dominant ideas coming into the 21st century. It was human hunters, it was climate change. What they meant by climate change now was not a catastrophic climate change where you might have a drop of 7 or 8 or 10 degrees in a matter of weeks or a few months. It was a climate change that would have been stretched out over 1,000 years, causing, shifting vegetation patterns and whatever. When the spruce trees shifted north, somehow the mastodons weren't able to move as fast as the spruce trees to get, from lower latitude southern United States up to the Canadian border. And so they died out. I mean, basically, that's kind of the theory. As far as the last time I checked, elephants, I would think, could keep up with a shifting forest biome. But anyways.
Right, yeah. It seems like trees probably can't move as fast as something that can walk, right?
as a general rule.
Right, yeah, as a rule.
Yeah, as a rule. So those were the two competing theories. So when we say climate change, if I would say, yeah, climate change was clearly involved, but not a climate change that takes 1,000 years, a climate change that takes maybe a year or 2 years to shift from interglacial to glacial conditions and back again, right? Now, that kind of a climate change, clearly, it could knock out the forest, and then what happens to the whole chain, the whole food chain in that forest? Well, it's going to
collapses.
Yeah. So, but the thing is you've got climate change now. Okay, well, after Greenland ice cores, okay, so we've got these massive spasms of climate change around, at the Younger Dryas boundary transition. We've got massive, at the Younger Dryas. So at the beginning of the Younger Dryas, at the end of the Younger Dryas, right? At the end of the Younger Dryas, it's the YDB Younger Dryas pre-boreal, which is the name of the period that comes immediately after the Younger Dryas, just as the Alarod was the period that came just before the Younger Dryas. Then, of course, you have the Older Dryas, which we haven't talked about, which wasn't as severe, but it was followed by this 14,600-year warming spike, which I think was probably responsible for the first rapid sea level rise that was a consequence of the accelerated melting of the ice sheet. And then you had the Older Dryas, then you had this gradual warming, and then you had the Younger Dryas that interrupted the gradual warming that would have been the result of changing geometries between the Earth and the Sun. So this would have been a much more prolonged, slow, which had all the earmarks of being related to the Milankovitch ideas of global change, because this continually changing amount of radiation impinging upon the Earth, which is due to the changing orbital geometries. The orbital geometries were shifting, say, between 14 and 13,000 years ago, which would have implied that the planet was warming, and the evidence suggested it was, because we see boreal forest shifting north, deciduous forest following right after. We see the first major recession of the ice sheet, and it's becoming rather balmy. Right now, all of a sudden, boom! At 12,900, that's interrupted, and within a matter of a year, like boom, back into full glacial cold. Right. So now we've got this massive climatic spasm that was recognized by 1992, 1993, after the JISP and GRIP ice expeditions extracted the two cores from the summit of Greenland. So then the question then becomes, well, okay, we could say that, this contributed to this or that. It certainly could have contributed to the megafaunal extinctions. But here's the question: what caused that climate change? We can't just say, the climate changes, it suddenly warmed up by 8 degrees centigrade within 5 years, without going, well, what is driving that change? See? So all of these factors kind of came together in the 2000s, and some scientists began trying to look outside the box to think there must be other explanations. So, for example, one of the ideas was that I think that there was a nearby supernova or a galactic. Oh gosh, it was actually Firestone's first iteration of his idea, but then that evolved because once they took a look at the boundary layer, which in so many places, as Vance Haynes pointed out, had this black matte layer. So then when they went back, they took a closer look. That's when they began to find the proxies.